Hello, welcome to Organic Chemistry lectures delivered by Sheetal Bhatkurki. Today I will be talking about addition reactions. The intent learning outcomes of this session will be, we will be able to identify certain electrophile which are adding across multiple step, which are involved in the multiple step reaction. We will be able to predict the mechanism of electrophilic addition reactions. Also, comparing the stereochemistry of electrophilic reactions. In nature, we have seen the existence of many varieties of compounds. Among such is the unsaturated hydrocarbons. So what are unsaturated hydrocarbons? They are the molecules, they are the hydrocarbons having double or triple bond in them. So there are ample of examples available in the mother nature, such as we find allicin, which is present in the garlic. The odor that we obtain for garlic is because of the allicin. Similarly, geranyl is being present in a high percentage in the rose, which is widely used in the perfume industry. So do alpha farnesene, which is waxy in nature, is widely used to apply for the apple skin and many other fruits, such that it do not allow evaporation of water or moisture content is avoided. Alkenes are the special class of compounds which are widely used in chemical industry. The two most important industrial alkenes, ethylene and propylene, are widely formed from cracking petroleum and are used as starting material for preparing wide variety of compounds. Every year, over 200 billion pounds of ethylene and 70 billion pounds of propylene are produced globally and used to make many compounds, which includes polyvinyl chlorides, polyglycols, isopropyl alcohols, ethylene oxides, etc., which have a very good characteristics, physicochemical characteristics. Because of their physicochemical characteristics, they are widely used in industry for different applications. All of those which I talked a few minutes back are made up of ethylene molecules. So what exactly are ethylene molecules and how do they react? Ethylene molecules are those which will undergo addition reactions. So whenever there is a electrophile and a nucleophile generating reagent, which will, the electrophilic part of this reagent will add across the double bond, because double bond is nucleophilic in nature, it has nucleophilic characteristics. So to recall what is electrophile, electrophile are the electron deficient species, they are electron loving species, therefore they will be always in search of electrons. Nucleophiles are those species which are negative species, which have electrons or which are nucleus loving and are ready to share their electrons to the pore centers. So in our case, the alkene itself is nucleophilic in nature, and we see that any electrophile which has been present in the reagent will be added across to the double bond, leading to the formation of a new sigma bonds. So with the consumption of one pi bond, two new sigma bonds are generally formed in case of an alkene. Whereas if it is a triple bond, that is alkyne or vinylic carbon, then a triple bond, with the consumption of a triple bond, there will be formation of two sigma pi bonds and one pi bond remains as it is, until unless there is excess of reagent. If excess of reagent is present, then all the double bonds, triple bonds which have been present are broken down to corresponding sigma bonds. So this is what exactly addition reaction is. Necessarily in an addition reaction, a double bond has to be broken down to a sigma or a single bond character. Now, addition reactions and elimination reactions to certain extent go in a reverse way. They are in the reverse way. If we see the forward direction indicating addition, wherein I am adding across one hydrogen and a halide, X is equal to halide here. But the same product, if I am going in a reverse way, then I get back my pi bond, which is nothing but a elimination reaction. Now, which one dominates over the other is depending upon the thermodynamic perspective. So, if we look into the thermodynamic perspective, the two reaction represents an equilibrium, that is temperature, they are temperature dependent. Addition is favored at a low temperature while elimination is favored at a high temperature. To understand the reason for this temperature dependent, let us recall the sign of delta G. Delta G determines whether the equilibrium favors the reactants or the products. If delta G must be negative for equilibrium to favor products, the sign delta G depends on two terms. Delta G is equal to enthalpy term and the entropy term. Now let us consider the term individually. Begin with the enthalpy term, delta H. Delta H in many factors contribute to the sign and magnitude. But the dominant factor is generally bond strength. If we compare the bond strength here, now the reactant has a pi bond and a sigma bond, which are broken down to form a new bond, which is a two new sigma bonds. So, in nature sigma bonds are much more stronger than the pi bonds. So, if we calculate bond broken minus bond formed is equal to 160 kilocalorie per mole minus 185 kilocalorie per mole, that accounts to minus 19 kilocalorie per mole. That means the bond being formed are stronger than the bonds being broken. Let us consider now the delta S, right? The entropy term minus T into delta S, entropy term. This term will always be positive for addition reaction. It's because two molecules are joining together to produce one molecule of the product. Let's see in the next slide. The two molecules are going to produce one molecule of the product. So, this represents a decrease in entropy and delta S have a negative value. The temperature component T measured in Kelvin is always positive. As a result, minus T into delta S will be positive for addition reaction. Now, let us combine both the enthalpy and the entropy term. The enthalpy term is negative and the entropy term is positive. So, the sign for delta G for addition reaction will be determined by computation between the two terms. In order to get delta G to be negative, the enthalpy term must be larger than the entropy term. This computation between the enthalpy term and entropy term is temperature dependent. At low temperature, the entropy is small and the enthalpy term dominates. As a result, delta G will be negative, which means that products are favored more over the reactants, wherein the equilibrium constant K will be greater than 1. In other words, addition reactions are thermodynamically favorable at low temperature. However, upon increase in the temperature, the entropy term will be larger and will dominate the enthalpy term. As a result, delta G will be positive, which means that the reactants will be much favored over the products and the equilibrium K will be less than 1. In other words, reverse process will be thermodynamically favored at the high temperature, and the reverse process is elimination reaction, is nothing but the elimination reaction. For this reason, addition reactions has to be carried out at low temperature, sometimes even below room temperature we do carry out the addition reactions. Now, addition reactions are further classified into two types, nucleophilic addition and electrophilic addition. So, depending upon the reactant, what would be the incoming reagent, whether it is electrophilic in nature or it is in nucleophilic in nature. So, based on that and the reactant, we classify them into electrophilic addition and nucleophilic addition. Now as I am dealing with alkene, alkene itself is a nucleophilic in nature, therefore I would like to add a electrophile towards the alkene which is nucleophile. Therefore the terminology comes electrophilic addition. The incoming group is a electrophile there, the incoming ion is a positive ion there. Why is it so? Because my alkene itself is having the electron density, therefore it would act as a nucleophile in nature. So, I have already recalled what is electrophile and what is nucleophile. Please note the arrow mark should be always from the electron rich center towards the electron poor center. So do in here the movement of arrow should be from the pi bond to the electrophilic nature, which is represented here in the slide as Y plus. So, when I take a neutral reagent which will definitely get hydrolyzed to positive and negative charge, the positive charge here is electrophile and the negative charge here is the nucleophile. Now because my substrate molecule is a nucleophilic in nature, so electrophile would be easily attacking, or I can say that nucleophile will share their electron towards the electrophile, and thereby a new sigma bond is being formed there by breaking the pi bond, existing pi bond. Mechanism of addition, if we see, then first step is the pi electron attacks the electrophile. So the pi electrons are ready to share their electron towards the electrophile and lead to a formation of a intermediate, which is a carbocation intermediate. I'll just now say what is carbocation and what are the stability of carbocation in a couple of minutes. In the second step, the formed carbocation is not stable, right? So we need to attain its stability. Therefore, nucleophile will attack the carbocation, the other part of the reagent which is present will attack this carbocation which is formed in the reaction course, leading to the formation of a stable product. Thereby we see that the electrophilic nature and the nucleophilic nature of the reagent has been added across a pi bond. Therefore I say with the consumption of one pi bond, there would be formation of two new sigma bonds. So this is a basic general mechanism of addition reactions. The first step is the electrophile, the pi bond attacking the electrophile, thereby leading to the formation of a carbocation, and second step, the nucleophile will attack the carbocation and share its electron, thereby leading to a formation of a neutral molecule. Therefore, a pi bond is broken down to form two new sigma bonds. Stability of carbocation is an important factor when we attain this intermediate in the reaction course of any addition reactions. To recall, we know that the tertiary carbocation is stable, most stable over the secondary over the primary, and primary over the methyl cation, all because of the positive inductive effect of the alkyl group, which are readily donating their electron towards the carbon center, to the carbocation center. Therefore, tertiary carbocation, which bears 3 alkyl groups, is much more stable than the secondary, which has 2 alkyl groups, compared to the primary, which has only 1 alkyl group, and compared to that the methyl cation, which do not have any alkyl groups. Therefore, is the least stable in nature. So, anywhere in the reaction course, when we attain the intermediate carbocation and there is a possibility of rearrangement, a primary possible to rearrange to a secondary, or a secondary possible to rearrange to a tertiary, if there is any possibility, then necessarily we have to do that and proceed to obtain the correct product. In case if there is no any possibility to attain, then the same product can be proceeded. We can write to only one product there. In that case, such examples we are going to see in coming up slides. There are various kind of electrophilic addition reactions that has been seen in many reactions. In multi-step reactions also we come across many kind of addition reactions. Please note what is being added across is clearly mentioned that in the addition reactions. For example, when I say halogenation, the terminology itself is clear that halogens are going to be added across the double bond. For example, when I say halohydrine, halogen and a hydrine is a OH molecule, right, is being added across a double bond. So do hydrohalogenation, where a hydrogen and a halogen is added across a double bond, leading to the formation of a single sigma bonds, two new sigma bonds. So generally the term is represented by the what is being added across. So these are the various kind of electrophilic addition reactions which we would be looking further in our discussion. Let us take up the first reaction, that is hydrohalogenation. As I spoke about the terminology, what is being added here is that hydrogen and a halogen is added across. Generally we represent halogen with the X notation, therefore here it is written as HX. HX is a hydrogen with a halide. For example, I would take HCl or a HBr or a HI, right. So that is the reagent that I am going to use, and that is going to split as H plus and Cl minus. So H plus is going to be electrophilic in nature, and Cl minus, because of its electronegativity, would be attaining minus charge on it. Therefore H plus would be electrophilic and Cl minus would be nucleophilic. Now let us see how the addition will be happening across a symmetrical alkene. So the first example represents here a symmetrical alkene. When a symmetrical alkene is there, then you add the electrophile to either of the carbon, generating a carbocation. It doesn't make much difference there because we end up into a same product. So the reaction is carried out at minus 30 degrees centigrade. As I said, addition reactions are generally preferred at a low temperature, therefore lead to the formation of a monobromo substituted product there. So herein hydrogen and a bromine is added across a double bond. The same when there is an unsymmetrical alkene, if I introduce a vinylic group at the second carbon here, then it becomes unsymmetrical alkene. And during unsymmetrical alkene, we have a question that the electrophile, will it add to the second carbon or will it add to the third carbon? So the two green shades that has been indicated, where will the halogen be added across? The hydrohalogen will be added across, and the first species that is going to be added is the electrophile. So H plus, where will it go? Depending upon where the H plus go, then the Cl minus would like to come and attack, right. So accordingly, here there are two possibilities. It can go to this carbon or it can also go to the other carbon, that is second carbon and the third carbon. Which one is more preferred? It depends on the halide, which hydrohalide I am going to prefer. In this case, the one of the carbon, that is C2 carbon, is less substituted carbon, whereas C3 carbon has a methyl group extension, therefore it is more substituted carbon. Now the incoming electrophile or the hydrogen that is going to come will go to that particular carbon which has less substituted groups, So it will go to that particular carbon which has less substituted groups. So do here, it is the second carbon which is less substituted, therefore the electrophile will be added across towards the second carbon, thereby generating a carbocation at the more substituted carbon. Recall, I just now said the more the substituted carbocation, more is the stability. Therefore, it will be the more stable carbocation formed there, and in the next step the incoming or the nucleophile will share its electron to this more substituted carbocation formed, leading to the formation of a more stable product. Therefore, the halide will, now hydrohalogens are added across the double bond. Remember, the first incoming group, that is electrophile, is added to the less substituted carbon, thereby generating a more substituted carbocation, which is more stable. And next the nucleophile will share its electron towards the more substituted or the more stable carbocation formed, thereby leading to a formation of a stable product. So, in 1869, Vladimir Markov, a Russian chemist, investigated this mechanism and gave across a rule which we call it as Markovnikov rule. And accordingly to the rule, when there is an unsymmetrical substituted alkene which reacts with the hydrogen halide, the hydrogen will add to that particular carbon which has greater number of hydrogens or lesser substituted methyl groups, and the halogen will add to the having fewer hydrogen substituents. Therefore, will lead to the formation of a more stable carbocation. Once the more stable carbocation is formed, the incoming nucleophile will be added towards that more substituted or the more stable carbocation, leading to the formation of a major product. Let us look at the mechanism. So let us take up this example and try to write the mechanism for this. As we have already dealt with the general mechanism, so we should be able to write the mechanism here. Let us take a cyclohexene. This is 1-methyl cyclohexene. That means there is a methyl group at carbon 1. Therefore, it is 1-methyl cyclohexene. So this when treated with HCl, so HCl will split as H plus, will get hydrolyzed as H plus and Cl minus. H plus is the electrophilic in nature and Cl minus is nucleophilic in nature. So now we know that alkene is nucleophile, therefore H plus is electrophile. So this pi bond, this alkene is going to share its electron to the H plus. Thereby the question comes, where should the H add, to the carbon 1 or to the carbon 2? Yes, it adds across to the carbon 2, not at the methyl substituted, because it is going to lead to the formation of a more carbocation when it is added across the carbon 2. Therefore, we get a 2-cyclohexene 1-methyl carbocation. This carbocation is more stable or carbocation because it is going to be a tertiary carbocation there, therefore it will be more stable carbocation, and further the nucleophile will share its electron to stabilize this positive charge carbon, and thereby a 1-chloro-1-methyl cyclohexane is being formed as a major product. Please note, it is not 2-chloro-1-methyl cyclohexane which is going to be obtained as a major product, but instead it is going to be 1-chloro-1-methyl cyclohexane as the major product. So this is the mechanism which is indicated here. Yes, similarly you can carry out for the 2 more examples wherein cyclohexene external double bond is there, wherein you are going to add across the hydrogen and the bromide ion there, right? I have written the product also so that you can easily work out for the mechanism. Now if we look into the stereochemistry of the hydrohalogenation, what exactly it says? Accordingly, if we look into the first step, that is in the first step, the pi bond will share its electron to the hydrogen, right. So the alkene is, in fact I can say it as alkene is going to be protonated there, leading to a formation of a carbocation intermediate, which is a more substituted carbocation, therefore is a more stable carbocation, and further the nucleophile is going to share its electron to the carbocation intermediate, leading to the formation of a product. Now the attack can be on either side. What is important to us to look into here is in which form will the product be formed, whether the configuration that we are looking for is going to be R configuration or is going to be S configuration. So we need to assess the stereochemistry. There are two enantiomers which are going to be produced in equal quantity, thereby we call it as racemic mixture because R and S are going to be formed here. The stereochemical outcome can be explained by the diagram that has been indicated here, which identifies that the key intermediate is a carbocation. So once the carbocation is formed, which is trigonal planar with an empty p orbital orthogonal to the plane, then this empty p orbital is subjected to attack by a nucleophile. The nucleophile can enter from either of the side, from the top side, lobe, above the lobe or below the lobe. Both the faces of the plane can be attacked with equal likelihood, and therefore we end up into a both enantiomers, nothing but the racemic mixtures. Both are in equal quantity, therefore we end up into a racemic mixture. Please note, the formed carbocation is trigonal planar with an empty p orbital orthogonal to the plane. Therefore, the incoming nucleophile can attack from both the sides, leading to the formation of both the stereochemical compounds, which we call them as enantiomers because they have opposite configuration, and when they are present in equal quantity both together, we call it as racemic mixture. Racemic mixtures can be separated, which we will deal with in another lecture. Now anywhere if there is any possibility of halogen, when we are doing a hydrohalogenation, if there is any possibility of the formed carbocation to rearrange itself to form a more stable carbocation, then please do that before you go to the next step, before you go to the second step. Look at this example wherein we have a hexene there, we have a double bond there and halohydrogen is being added across. So the formed intermediate, the first intermediate that is going to be formed is a secondary intermediate. Now this secondary intermediate can itself rearrange in such a manner that it can shift hydrogen there. Therefore, by just shifting hydride, right, it can lead to a formation of a more stable tertiary carbocation, more stable tertiary carbocation. Therefore, once the more stable tertiary carbocation is formed, then the nucleophile will attack that or stabilize that carbocation by sharing its electron and lead to the formation of a more stable product. So you can see that you are getting again mixtures there, 40% of 1-chloro and 60% of 2-chloro. Which one is more substituted product there? Obviously the second one, and that is a rearranged product because we are obtaining it only after rearranging a secondary formed carbocation to a tertiary carbocation. Therefore, it is more stable product that is going to be obtained. So similarly, we do have a question here. Can we write the mechanism for this? Right? Yes, we can write. Again, the same thing. Secondary carbocation is formed, which is going to be again forming a tertiary carbocation, leading to the formation of a more stable product. Work up for these two examples. So, Ricci selectivity of hydrogen halide additions, which follows Markovnikov rule. The various examples has been given here. So, first one is only one substituted, wherein we are able to get the 1-bromo substituted product or as the major product. Similarly, I am going to substitute now one of the hydrogen by another R group, right? Similarly, in the third one I have substituted one more hydrogen by R group, thereby I have 3 R groups, right? And the last one I have R groups in trans fashion, right? So both the products are equally absorbed. So in the first 3 example, only one product is obtained as a major product there, Whereas in the second one, if R and R dash are too different, then definitely we do observe the both products are going to be formed there, right? So please take up this example and do solve, write the mechanism. Let's look into the another set of example electrophilic addition reactions, and that is acid catalyzed hydration. Why this terminology comes acid catalyzed? Adding a water, hydration itself says adding a water molecule there, right? Hydrogen, H and OH across a double bond. This process is called as hydration. This process is called hydration. Why I am saying acid catalyzed hydration? That means I am going to use a catalytic amount of acid to carry out this addition reaction. That's why the term comes acid catalyzed hydration. So basically I am adding a water molecule across a double bond in presence of a catalytic amount of acid. Therefore, the terminology acid catalyzed hydration. The first two methods provides us a Markovnikov of addition, which I discussed. Now the third one, which I am trying to say, acid catalyzed hydration, is an example of anti-Markovnikov reaction. Is an example of an anti-Markovnikov reaction. Let us the reagent hydronium ion H3O plus represents the presence of both water and an acid source, such as it might be sulfuric acid or any other acid. These conditions can be shown in the following way. When I take an alkene plus water, on the bracket is my acid, leading to the formation of a alcohol, which is resulting in the major product, and it is represented as 90% yield. Therefore, it is an acid catalyzed hydration. The rate of acid catalyzed hydration is very much dependent on the structure of the starting alkene. In the table given here, if we compare the relative rates of the reaction, three reactions are indicated here, and we can see that the effect of alkyl substituent on the relative rate of the reactions, right? When it is a simple alkene, the relative rate is 1, but as I go on increasing the substitution at one of the carbon of alkene, then the rate of the reaction is drastically increasing. That is, with addition of each additional alkyl group, the reaction rate increases by many orders of magnitude. The OH group is installed at the most substituted position. These observations can be justified with a mechanism that involves a carbocation intermediate, a more stable carbocation intermediate. Let us see the mechanism. To support the relative rate, increase in relative rate of the reaction, let us support it with the mechanism. Let us take a alkene there, right? Alkene, basically first step is a proton transfer from the substituted or protonated water. So this is protonated, right? Therefore it is going to protonate now the alkene, right? Hydronium ion H3O plus, which is electrophilic in nature, and the alkene is nucleophile, therefore will share its pi bond and will to the one of the proton. One of the proton is been dragged, and it is going to lead to a formation of a carbocation. The formed carbocation, now water which is being present will function as a nucleophile and attack the carbocation intermediate. So once the carbocation intermediate is formed there, now I can call it as oxonium ion. Oxygen is bonded to bonded through a 3 sigma bonds there, having a lone pair of electron will attain positive charge. Therefore I call it as oxonium ion. Oxonium ion. Now in water also functions as a base and deprotonates the oxonium ion by pulling out one of the proton, Therefore proton transfer will happen and lead to the formation of a alcohol. The end product that we are going to get is an hydroxy group there, which is nothing but a alcohol group. So this is the mechanism. Now please note here, if I carry out it in a dilute condition, dilute acid, then I end up into the same product, that is alcohol, which has been shown in the mechanism. But if I use a concentrated H2SO4, then the same reaction the formed product can also be reverted back to an alkene and a water molecule, right. Therefore, we need to be very careful when we are using a acid. In acidic condition, the concentration of hydroxide ion is negligible, but the concentration of water is quite large, right. The proposed mechanism is consistent with the experimental observation that when we proceed via a Markovnikov addition, we saw for hydrohalogenation, because there is a strong preference for the reaction to proceed via the more stable carbocation intermediate. Similarly, reaction rate of the substituted alkene can be justified by comparing the carbocation intermediate in each 3 examples or 3 reaction cases. Reaction that proceed via a tertiary carbocation will generally occupy more rapidly than the reaction that proceeds via secondary carbocation more over the primary carbocation. Therefore, you can write the product and compare the rates. So, the major control over the equilibrium to attain a alcohol and alkene in the previous example, which I did just now, I show that if there is more concentrated acid, then I can get back to my alkene, right. Therefore, that I would support it with the stereochemistry. Thermodynamic arguments were represented to explain why low temperature favors addition, right, while high temperature favors elimination. For acid base catalyzed, either it is a dehydration or a hydration reaction, there is yet another way to control the equilibrium. The equilibrium is sensitive not only to the temperature, but also to the concentration of the water that is being present. By controlling the amount of water present, one side of the equilibrium can be more favored. So do in my previous reaction, right, the dilute H2SO4 when I took, the more of water quantity is being present in my reacting species reaction course, leading to the formation of a more stable alcohol. But when I take a more concentrated sulfuric acid, the water concentration is going to be less there. The water concentration is going to be less there and leading to the formation of a more favored alkene as the product. Control over this equilibrium derives from an understanding of Le-Chatter's principle. Recall Le-Chatter's principle, which states that a system at equilibrium will adjust in order to minimize any stress placed on the system. Consider now for this example, right, that water is on the left side of the reaction, right. How would the introduction of more water affect the system? The concentration would no longer be at equilibrium and the system would have to adjust to re-establish new equilibrium concentration. So, the introduction of more water will cause the position of equilibrium to move in such a way that more of alcohol is being formed. Therefore, dilute acid is used to convert an alkene to an alcohol. On the other side, if I want an alkene from an alcohol, then the removal of water from the system could favor the formation of an alkene. So, in summary, the outcome of a reaction can be greatly affected by carefully choosing the reaction conditions and concentration of the reagents. In this case, it was water as the reagent. So, based on the temperature and the concentration of the water, I was able to control the reaction moving from an alkene to an alcohol. But if I want to do in the reverse way, then and obtain an alkene, then again I would decrease the concentration of water and increase slightly the temperature such that I would get back my alkene. Please note the stereochemistry chemical aspects of the acid catalyzed hydration. Let us take up one more example here, right. Already the product has been written, I just want to show you the mechanism. The mechanism indicating that there is a formation of a carbocation which is a more stable carbocation. So do not go to form a new carbocation there, because obtained carbocation itself is a more stable carbocation, right. Further, the water molecule which acts as a base will help my oxonium ion to give away one of the proton and therefore attain alcohol, which is a tertiary alcohol, which is more stable alcohol. Few more examples to do at home. Let's go for one more set of reaction, which is oxymercuration. The terminology oxymercuration and demercuration means I am going to add oxygen and mercury, and at the same time I am going to remove the oxygen and I am going to remove the mercury. That is why demercuration, whereas oxygen remains itself, I am removing only the mercury, therefore demercuration, right. Please understand terminology. Herein, in case of an alkene, when an oxymercuration is added across, right, this is again acid catalyzed reaction, wherein we would be using a little quantity of acid here as a catalyst, right, will lead to the formation of an intermediate, which is mercury cation, or it leads to an intermediate mercury cation. This mercuric cation will further, further upon removing the mercury, demercuration will lead to the formation of a alcohol. To understand this process, we must explore the reagents that are being employed. The process begins when a mercuric acetate, so here is my mercuric acetate which is shown here, is in equilibrium forming a mercuric cation. So mercuric cation with the acetate ion is being obtained there. The mercuric cation is a powerful electrophilic in nature. It is electrophilic in nature and is going to be attacked by a nucleophile such as my alkene in this example. When a pi bond attacks a mercuric cation, the nature of resulting intermediate is quite different from the nature of intermediate that has been formed when a pi bond is simply protonated, right. Let us see the mechanism. Here is the mechanism. So this is the first form which I am indicating, that when a simple pi bond is being protonated, right, the carbocation is obtained in this way, right. Whereas in case of oxymercuration, demercuration, when a mercuric acetate is the electrophile, which is a strong electrophile present, then the pi bond will attack this mercuric cation, leading to a formation of a mercurinium ion, which is going to acquire a bridge intermediate, right, a 3 bridge intermediate it is going to obtain, which we call it as mercurium ion. So when the nucleophile is been present, the nucleophile is going to attack at that particular carbon. At the same time, the mercury has to be the mercurium acetate. The formed bond, which is not a true bond, will be broken down, leading to a formation of the introduction of the nucleophile. Further, this is oxymercuration done with where nucleophile is added across the double bond. The first is electrophile, that is mercury acetate, which is added across a double bond, and double bond is broken down, leading to a formation of a mercurium cation. Further, nucleophile will come and share its electron to the one of the positive charge of the carbon, but not the positive charge of the mercury, and thereby leading to a break that bond, that superficial bond which has been formed there, right. This is oxymercuration. Still one more step has to be carried out, and that is demercuration has to happen. So demercuration will happen, leading to a formation of a alcohol as the end product. So the more substituted carbon atom bears a positive charge rather than a fully positive charge. Please note that, right. This intermediate will not readily undergo any kind of rearrangement, carbocation rearrangement, but it is still subject to attack by a nucleophile. Therefore nucleophile attacks, and once nucleophile attacks, it leads to the mercury to be removed. Therefore demercuration should happen, which is accompanied with a sodium borohydride. So using sodium borohydride, I can remove the mercury there. Therefore demercuration happens there, right. There is much evidence that the demercuration will occur via a radical process. So the net result of this is addition of hydrogen and a nucleophile across the alkene using mercury and sodium borohydride to remove the mercury, added mercury. So this obeys Markovnikov rules. So you can see the mechanism clearly written here. Whatever I explained, the same mechanism is rewritten here in the form, right? Acetate ion attacking a pi bond, therefore a bridge structure is formed, which is a mercurium ion. Further, this is you obtain, so water molecule which is acting as a base here, right, will drag the proton, one of the proton, and lead to the formation of a alcohol. So alcohol is formed, but however I need to remove this mercury acetate, therefore I use sodium borohydride, which is a source of hydrogen, therefore will lead to the formation of my alcohol. So you can see that the alcohol is being formed here. Then let us see the next set of example, hydroboration. The process is called hydroboration because I am adding here hydrogen with the help of boron and followed by oxidation, So simultaneously I am doing a oxidation also here, right. So now this do not obey Markovnikov rule, therefore it is an anti-Markovnikov addition. It is an anti-Markovnikov addition. So OH group at a less substituted position, it is going to be installed rather than a more substituted position. If any nucleophile is being introduced at a more substituted center, the carbon center, then it would definitely obey a Markovnikov rule, but in case if it is installed at a less substituted position, then it would obey anti-Markovnikov addition. So note here that the hydroboration oxidation will happen through anti-Markovnikov additions, right. The stereochemical outcome of this reaction is also of particular interest. Specifically, when two new chiral centers are formed, the addition of water, that is H and OH, is observed to occur in a way that places the hydrogen and OH on the same face of the pi bond, leading to the formation of enantiomers. So such an addition we call it as syn addition on the same side, therefore we call it as syn addition. The reaction is said to be stereospecific because only 2 of the 4 possible stereoisomers are formed. That is, the reaction does not produce the other 2 isomers which would not form there, resulting in addition of adding hydrogen and OH to the opposite faces of the alkene, whereas the added hydrogen and OH are always on the same face of the pi bond, therefore syn addition. So here is the stereochemistry which is indicated here. The structure of borane BH3 is similar to that of a carbocation, but with the charge, without any charges. I have not written any charges, empty p orbitals you can see there, right. So first one is the carbocation with a charge, positive charge, whereas boron without any charge, but both of them do bear empty p orbital, right. The boron atom lacks an octet of electron and is therefore very reactive. In fact, one borane molecule will even react with another borane molecule to form a dimeric structure called as diborane. So you can see the structure of diborane there. The dimer is believed to possess a special type of bonding that is unlikely happening in any other resonating structures, right. So we have also written the resonating structures there. So you can see that 2 electrons are spread over the 3 atoms, right, spread over the 3 atoms. So such bonds are called 3 centers 2 electron bonds. We call them as 3 centers 2 electron bonds. So in the world of organic chemistry, there is another example of 3 center and 2 electron bonds. However, we will not encounter any other example in this context right now. So borane and diboron coexist in the equilibrium, right. This equilibrium is lies very much to the side of diborane rather than a borane, leaving very little borane present at the equilibrium. So it is possible to stabilize the borane, thereby increasing its concentration at equilibrium by using a solvent such as tetrahydrofuran. So such as using tetrahydrofuran here. You can see that, right? Boron with a tetrahydrofuran reacting, which can donate tetrahydrofuran can donate the electron density to its empty p orbital of borane. So empty p orbital of borane is being filled. Now, although the boron atom does not receive some electron density from the solvent, it is nevertheless still very electrophilic in nature and subject to attack by the pi bond of an alkene. So don't be under the impression that it would be attaining nucleophilic in nature by taking the lone pair of electrons. No, it will still be electrophilic in nature, therefore is susceptible to undergo electrophilic addition reaction across the pi bond. So mechanism is indicated here. The first is electron concentration. Please note that attack of the pi bond triggers a simultaneous hydride shift. However, this proceeds does not have to be a perfectly simultaneously. It may be in some fraction of second variation. As the pi bond attack the empty p orbital of boron, one of the vinylic positions can begin to develop a partial positive charge, that is delta positive charge. This developing delta positive then triggers a hydride shift. So that's how hydride shift is taking place there. Once a hydride shift is taking place there, leading to a formation of a trialkyl borane, the formed trialkyl borane will happen, right? The next step is a oxidation which has to happen there. So you can see oxidation happening there. pK value of this peroxide is 11.8, right? Whereas the nucleophile, that is OH minus, a hydroxide ion, which is a nucleophile and base 2, will drag one of the proton from the peroxide. Proton transfer will happen, leading to a formation of a ion there, right? Forming a hydroperoxide ion there with water molecule being eliminated. So the formed ion is a nucleophilic in nature, will go and attack the boron. The hydroperoxide functions as a nucleophile and will attack the trialkyl borane now. So once it is attacking a trialkyl borane, oxygen and boron is going to establish a new sigma bond there, which will lead to the formation of a rearrangement, right? So OH minus causes the expulsion of a hydroxide ion to happen. OH minus expulsion happen there, leading to the formation of the first 3 steps of oxidation are repeated, converting the trialkyl borane into a trialkoxy borane. So across the alkyl group of borane is the oxygen add-on, therefore it is trialkoxy borane. A hydroxide ion functions as a nucleophile in the next step and attacks the trialkyl oxyborane, leading to the further loss of a leaving group, which is OR group, that is alkoxy group is eliminated out, right? And alkoxide ion is eliminated out, removing the negative charge on the boron, and the alkoxy ion is nucleophilic in nature, will drag one of the proton from the water molecule and lead to the formation of a stable molecule alcohol there, So this is the overall mechanism of the reaction, right? So you can see that steric consideration has to be thought, right? So transition state, in case if it was following a Markovnikov addition, then more crowded scenario is seen there, therefore it is not favored. Instead it would like to undergo through a transition state which is less crowded there, therefore will lead to a anti-Markovnikov addition, So this transition states will clearly give us the stereochemical outcome. So hydroboration oxidation is essential to consider that the number of chiral centers that are created during the process. If there is no chiral centers are formed, then stereo specificity of the reaction is not observed. But if there is any formation of a chiral center, then definitely we are going to acquire the stereo specificity of the reaction. So you can see here, one new chiral center is being formed there, right? In this case we are ending into enantiomers, that is because of the syn addition can take place from either of the phase, from the top phase or from the bottom phase, and leading to the formation of enantiomers in equal proportions. Therefore, it is syn addition, right? Anti-Markovnikov syn addition. So also we call it as enantioselective addition depending upon the circumstances. Further, only one of the enantiomer predominates, then it becomes enantioselective addition reactions. Let's take up one more example here. What would be the product formed? The product formed would be an alcohol added across to a less substituted, or here at this position it would be formed, right? Yes. So at the less substituted, the alcohol is going to be formed. Syn addition process, it is stereo specificity of the reaction is syn addition is relevant. While drawing, you need to see that you are attaining a syn addition. Few more examples to carry out at home. Yes. Now let's look into one more example, that is catalytic hydrogenation. The terminology itself is very clear, that addition of molecular hydrogen H2 across a double bond in presence of a metal catalyst. So we are going to use a metal catalyst here. So in this given example, we are using platinum as the metal catalyst. Paul Sabatier was the first to demonstrate that the catalytic hydrogenation could serve as a general procedure for reducing an alkene, and his pioneering work in 1912 he received the Nobel Prize for this work. Stereo specificity of catalytic hydrogenation. What kind of hydrogenation catalyst I am using? Homogeneous and heterogeneous catalyst, both can be used in the reaction, right? In this example, wherein you are able to see that when two new chiral centers, that is two new chiral centers, there are four possible stereoisomers produced. Two of them are, two pairs of enantiomers are observed. Actually, the first pair is observed, whereas the second pair is not at all observed, right? That means in the reaction course, though we expect theoretically the four product to be obtained, but only two products are obtained practically, whereas the other two are not obtained. It's because of the result of the syn addition, right? Syn addition will happen, therefore only the two enantiomers are obtained. Variety of metal catalysts can be used. Platinum, palladium, nickel are generally used as the metal catalysts, right? Which will definitely interact with the surface of the molecular hydrogen, right? This metal catalyst will interact with the molecular hydrogen effectively by breaking the hydrogen-hydrogen bond and forming a individual hydrogen atom absorbed on the surface of the metal. The alkene coordinates with the metal, so you can see that the alkene is coordinating with the metal surface, and the surface chemistry allows for the reaction between the pi bond and the two hydrogen atoms, effectively adding hydrogen across the alkene, adding each hydrogen across the alkene. In this process, both hydrogen atoms are added to the same phase of the alkene, therefore syn addition. Stereo specificity is syn addition. In any given case, the stereochemical outcome is dependent on the number of chiral centers formed in the process. So if there is one chiral center, then both enantiomers are formed, and if there are two chiral centers, the requirement of syn addition determines which pair of enantiomer is going to be obtained. Let us see one more example here. So, any guess what would be the product? Yes. So, hydrogen is going to be added across the double bond. So, each hydrogens are going to be added across the third carbon and the fourth carbon respectively. So, you can see, yes. So, added across the, so we get two new chiral centers. Few more, these are the two possible enantiomers. Only two possible enantiomers. The third and fourth enantiomers are not possible. Some more examples to work out. This is anti-addition. You can see that anti-addition happens here through formation of a bromonium, cyclic bromonium ion. So, the next reaction is halogenation and halohydrine. Halogenation, two halogens are added across the pi bond, right. Halohydrine, hydrogen and a OH and a halogen are added across the double bond. OH and the hydrogen, OH and the halogen are added across the double bond. So, that is halogenation reaction, which is an anti-addition reaction, right. Halogenation of an alkene is only practical for the addition of chlorine or bromine. The reaction with the fluorine is too violent and therefore, we do not carry out. The reaction with iodine often produces a very low yield, right. So, chlorine and bromine are the more preferred one. The stereospecificity of halogenation reaction can be explained in case where there are two new chiral centers going to be formed and formed new, it is because two halogen atoms will attack from the opposite sides. One, they do not attack from the same side. If one is attacking from the front side, the other one will attack from the back side. That is, the first incoming Br plus will attack from the front side. If it is from the front side, then Br minus, that is bromide ion, will attack from the back side. Therefore, it will lead to the formation of an anti-addition, not a syn addition. Please note, from the opposite faces they are attacking, right. So, anti-addition is formed here. And this goes through a cyclic intermediate, which is a cyclic bromonium intermediate. So, you can be clearly shown here the cyclic bromonium ion formation, right, nucleophile attack plus the loss of leaving group leading to the formation of a bromonium ion. The second again the bromide ion, which is nucleophilic in center, can attack from either of the side, from the front side or from the back side, leading to the formation of the anti-addition. So, this step, the second step, is an SN2 reaction, and we know that in a SN2 reaction it is the backside attack which is more stereochemically favored, therefore lead to the formation of a anti-addition. The same has been represented here again. Regiochemistry of halohydrines. Let us see the regiochemistry of halohydrines. When bromination occurs in a non-nucleophilic solvent such as in water, such as chloroform, the result is the addition of bromine across the pi bond. However, when the reaction is performed in presence of water, then the bromonium ion that is initially formed can be captured by a water molecule rather than a bromide molecule. So, the intermediate bromonium ion is high energy intermediate here and will react with the nucleophile that it encounters immediately. When water is a solvent, it is more likely that the bromonium ion will be captured by a water molecule before having a chance to react with the bromide ion, thus resulting oxonium ion, which is then deprotonated to give the product. So let's see one more example here quickly. So this is alkene reacting in presence of bromine with the water molecule. As rule we would expect that two bromine should be added across the double bond, but we know that there is water, therefore it will now it is going to, as I said previously, right, the water molecule is going to capture the bromide ion, leading to formation of the electrophile would be now OH minus, and water acting as a nucleophilic in nature and will assist the OH to be added across the carbocation there. So this is how it is going to be formed. Therefore, halohydrine. Halo bromine is an halo here, hydrine OH. So water OH and the bromine halogen is added across the double bond. That's why the terminology halohydrine. Few more examples to carry out at home. One more important mechanism, free radical addition of hydrogen bromide to alkene, which takes place in presence of a peroxide. Therefore, we call it as peroxide effect. The phenomenon was developed by Karash, therefore we call it as Karash effect also. Under the same condition, but the opposite Regier's selectivity is obtained, therefore it is anti-Markovnikov addition, an example of an anti-Markovnikov addition. So you can see that the alkene reacts in presence of hydrogen bromide. When there is no peroxide, then obtained product is a Markovnikov product, Markovnikov's adduct, whereas in presence of a peroxide we get a anti-Markovnikov addition or a product. Let's see, the Karash proposed that hydrogen bromide can add to alkene by two different mechanisms, both of which are in modern terminology Regier's specific. First mechanism, electrophilic addition, follows Markovnikov rules, no peroxides are present. Second mechanism is the free radical chain which proceeds through the free radical mechanism. Let's see here. First step is the dissociation of the peroxide into alkoxy radical. So peroxide will split into two alkoxy radical. The next step is the propagation step, which continues. Step 2, hydrogen atom abstracts form a hydrogen bromide by an alkoxy radical. So the formed alkoxy radical is clearly shown here, right, is going to react with the hydrogen bromide, and this hydrogen bromide is now going to lead to a formation of one more free radical, that is bromine atom. So the chain propagation starts with the bromine atom formation. Bromine atom will go and attack the, pi bond will share the electron towards the bromine atom, thereby forming a monobromo radical, right. This monobromo radical will further go and attack one more hydrogen bromide, and that continues till we propagate the step. In the last step, the termination has to happen, therefore we do terminate it by adding a bromine atom to give a primary alkyl halide. Please note, secondary alkyl radical is more stable than the primary alkyl radical, just like how carbocation, right. So alkyl radical abstracts a hydrogen atom from the hydrogen bromide to give a alkyl bromide product as shown in the step 4, in the above step 4. Similarly, we also observe electrophilic addition to alkynes. If we take only 1 mole of reagent, then from an alkyne we get an alkene. But if there is excess, then this alkene can also further break down to form a alkane. Mechanism involves initial addition of mercury ion here in this case, because I am using mercury chloride there, and subsequently trapping the vinyl cation introduces the chloride, and then carbon mercury bond is rapidly cleaved by the proton by an Se2 mechanism. So this is the mechanism which has been indicated here. Addition of carbene to alkyne is also an example of addition reaction itself, wherein we do get a cyclopropane ring which is unstable and which opens up further. There are 3 classical ways to generate carbenes. Please note, diazomethane, Simon-Smith reaction, and alpha elimination from haloforms. Right now I am not saying them. So with this, I would like to end up my session. I spoke about electrophiles and what is electrophilic addition reactions. I also indicated the regioselectivity wherever the regioselectivity was expected. Selective reactions I spoke about, and I spoke about a few reactions like hydrogenation, halogenation, hydrohalogenation, and oxymercuration, demercuration, and hydroboration oxidation, and all the stereochemistry of the reaction was also discussed. So with this I complete my addition reaction, electrophilic addition reaction. Thank you.